story in which I am telling you starts with spin glasses. Now, spin glasses are, you put, for example, atoms of iron diluted in a matrix of gold, and for reasons that have to do with solid-state physics, the interaction between quantum reasons, the interaction between the spins can be either ferro or anti-ferro, depending very sensitively on the distance. And because the positions of the atoms of iron are random, because this was obtained with a mixture, with an alloy, it's as if, everything is as if the sign of the interaction between these spins are random. So the first people who, first of all, it was observed that, and I think this is where the name spin glass comes from, this system has a glassy-like behavior with slow dynamics. So this is a system of spins, and so Sam Edwards and Phil Anderson proposed a model, which is called the Edwards-Anderson model, where you are in a lattice with nearest neighbors. You have spins that are plus minus 1. This is a square lattice in 3 dimensions, for example. And the interactions, Jij, can either be positive or negative. And you choose them at random. This is what is called quenched randomness. Quench means something that will not vary anymore. I do it when I construct my system, and then that's it. Just like the iron atoms don't move within the gold during your experiment. So these signs are fixed, but because there are plus and minus, the spins don't know very well what to do, because being all parallel, like in a ferromagnet, is no good, or anti-parallel, like in an anti-ferromagnet, is no good. So it's a messy situation, and the system has slow dynamics and has a complicated behavior, but it has a phase transition, a spin glass phase transition. So in terms of temperature, you measure any quantity, and you have a second order phase transition at a certain, which call critical. And the dynamics above is very uninteresting. The dynamics below is slow, and this is the glassy dynamics, and that's it. So nobody doubts that this 3-dimensional is difficult to solve, impossible for the moment. So Sherrington and Kirkpatrick and Scott Kirkpatrick proposed a version of this model. What you would do when you don't know what to do, then you do fully connected. This is typical of StatMech. You either do large dimensions or large number of components or fully connected. This is a universal trick when you're run out of technical ability. So this model with not nearest neighbors but now all is the Sherrington-Kirkpatrick model. And so they thought that it was going to be easy. And
will the couplings be different depending on the neighbor distance?
Now there is no longer any distance. Here it's only nearest neighbors.
Yeah, so for say 2 neighbors it's J, and for 3 neighbor interaction that will be a different.
There is no, in this one there is no 3 neighbor.
I'm saying, like, when you include the 3 neighbor interaction.
Oh, they would be different, yes. Yes, because it comes from a term that oscillates very much with the distance of the iron atom. Okay, so they thought it was going to be easy when it was, probably this was a suggestion of Sam Edwards, I think. They thought it was going to be easy. They tried it with a method that was originally proposed by Edwards. And the fact is that it wasn't so easy. They only managed to solve the high temperature phase, the statics, the equilibrium thermodynamics of the high temperature phase. And they realized that the entropy became negative below that temperature. So it's fortunate that they did this calculation, because this, with plus minus 1 spins, you cannot have a negative entropy. So they realized that their solution wasn't going to work, wasn't correct. By the way, the method they use, it's a replica trick. I'm not going to talk much about it, but it's a very arcane, I should say is the word. It's a very unusual way to do things. Okay, so then lots of people tried in the years that followed, I'm talking of the end of the 70s, to solve it below the critical temperature. And after many trials within the replica trick, finally what we know now is the correct solution was done by Parisi in a sequence of papers starting from the end of the 70s and ending at, say, 84 or something. The solution here is really a tour de force of intuition of things that are not quite rigorous, and you have to believe and you have to have the intuition to be able to follow. And then the interpretation of the solution is even harder, and really it is really a tour de force. And so much so that many people didn't believe it for a long time. Until now we have the rigorous solution. It coincides with Parisi's solution. So there is no, from that point of view, no more discussion. The only discussion that remains is whether the solution for the fully connected is, in some sense, the kind of solution you would have in 3 dimensions. And this, there's no agreement, and it's only numerical, and it's very hard. Okay. In any case, this model showed below the glass transition, the only glass transition there is, many minima, many states. This was a feature that already happened, and a complex behavior, difficulty to thermalize and so on. But this is spin glasses. So next step in this story is Derrida, in the beginning of the 80s. One of the things that came out from this solution is that the density of levels, if I look at how they are distributed, of energy levels, because there's plus minus 1 spins, this is discretized, goes like an exponential. So initially starts, and this is very much related to what Bulbul was saying, it goes like the number goes like e2, starts something like this with some coefficient. But they are correlated, and in a very complicated manner. What? Sorry?
Is that just for low energy?
Yeah, then the whole thing becomes some sort of, it's only linear for low energy. So then Derrida said, okay, I want a model that I can really understand, so let me just invent a model where I throw at random energies with a distribution that in fact he chose as a Gaussian. So choose 2 to the n levels, which is what you would have like this, and throw them with this Gaussian distribution. It's a synthetic model. There's no Hamiltonian if you want, but the Hamiltonian is given by this choice of 2 to the n energies. This seemed very easy. It's called the random energy model. It solved exactly this, has been beaten to death even more than the Sherrington-Kirkpatrick model. You can solve it with or without replicas, which is the nice thing. Of course, the results coincide, etc. Okay, what is the difference between this one and this one? That here the levels are uncorrelated. So you threw them as uncorrelated. This is how you made them. Turns out that then very soon it was discovered that if you did models like this, I'm staying at mean field level with p-spin interaction, provided that p is larger than 2, provided that p is larger than 2, you get a solution that is essentially of the same kind as the REM, and different from the one of Sherrington-Kirkpatrick. I'm going to explain these differences now. So p-spin and Potts models, this shouldn't surprise you too much, because when you have ferromagnets and you do 2 spin interactions, you get a usual ferromagnet. When you do 3 spin interactions, then you get a first order or 4 spin interaction, you get a first order. It's quite a standard thing that adding the number of interactions, p interactions, changes the nature of the transition. Here you get a glass with, I'm going to tell you now, different properties. And okay, that was it. And this one this generic model can be done with either plus minus 1, or if you want to make it a bit easier and you don't lose much, you can do it with a spherical constraint. Of course, this implies this, but this doesn't imply this. This is usually a trick that you do when you don't have any better techniques. So it helps technically. There's no excuse other than it helps you technically. But the phenomenology is exactly the same, so you can, from now onwards, think of continuous spins constraint in this. So, this was done, solved by several people, Mézard, Gross, David Gross, and then Gardner, Derrida, and lots of other people. And you get a phenomenology that is a little bit different, and on this one I will emphasize. Okay, this had started like a way of understanding and getting a cheap version of that, because that is very complicated. And it turned out the phenomenology and the nature of the solution was a little bit different, although you still have many solutions, you still have a transition, and now you will see that it's a bit more complicated than that. Now, I think this was the end of the 80s, Kirkpatrick, but another one, Ted, Tirumalai, which I should have put before, and for some reason I made a mistake. Tirumalai and Bolines said, for reasons that I'm going to explain now, that this model, which is a mean field model, which is happens to be a bit different in ways that I'm going to tell you now, to this one other, both are solvable. For a sequence of reasons, they guessed that this was the mean field version not of spin glasses, but of glasses, structural glasses. A class, at least, of these glasses, which are called fragile glasses, but think of hard spheres, Lennard-Jones gases, plastics, all the plastics you know. Okay. So this is, by the way, an amazing thing. All the developments in Europe concerning this were mainly technical, but it took people who knew more about liquids to make this guess. People who were closer to reality, and this would characteristically happen on the other side of the Atlantic. So now I'm going to tell you in what sense this model is different first, just so that you reconstruct the chain of guesses that made these people. Now, this thing now is rebaptized random first order theory, and this is what I'm going to describe. So, first thing compared to this one, if I do a plot of anything, but let me for the moment not specify, in temperature, I get a temperature where there is a thermodynamic discontinuity, just like before. The solution is of the kind but not quite equal to this one, and that's okay. Next thing, and this is a remarkable intuition, they asked, okay, can I do the dynamics of such a model? What would the dynamics of such a model be? This is why I took the trouble of introducing the continuous model. It's easier to write the dynamics for a continuous model. Well, the dynamics just attribute to it just the dynamics Udo did today. Plus a thermal bar. Okay, so this is the dynamics that normally leads you to equilibrium. Put this into the computer or wherever and apply it to this model with some Lagrange multiplier that keeps the constraint constant, and that's all. And when you do the dynamics, I am giving a slightly distorted account, but anyway, when you do the dynamics, you discover something remarkable, which is that the dynamics is okay here, but it has a transition at a different temperature, at a higher temperature. And the time scale here diverges. So the dynamics becomes infinitely slow at a different temperature. That's first remark, which if somebody would have stopped anybody else. But what happened is that when you look at the dynamics that you get close to this transition, turns out that the dynamics you're getting is what already had been proposed for glasses, and which is the mode coupling theory. So first thing they found is, wow, automatically and without having asked anything, I get this theory, which is a theory for structural glasses that had been in the market and people were using. This mode coupling theory has a transition, but everybody knew already that this transition is fake, is an artifact of the approximation, that it cannot exist really, for reasons that when you look at this model, it becomes transparent. I will tell you in a minute, but in a bit more than a minute, but this transition is an artifact. So what here becomes a divergence of the time scale, you have to reinterpret as a crossover. This you know, you have to accept. And the processes that happen here in this intermediate region, this is a region where in equilibrium nothing happens, but you get a hopping from state to state, which within this model is not permitted within mean field, but as you move out of mean field, you would have activated processes that would take you from state to state. So there is a dynamic transition and a thermodynamic transition, and we know that the dynamic transition is somehow fake, and that activated processes, meaning processes that are not mean field, would allow you to equilibrate even here. But they don't in the mean field problem. Yes?
So just trying to connect up to the kinds of landscape pictures you were drawing yesterday.
Yes.
TD would be where you would get.
Yes. From the point of view of landscape, here in this region, the picture that people do is that you have a basin of attraction like this. In this region, the basin fractures. You get essentially the same state, but now the basin fractures, and in this region, only a few of these are left. States are left. You're not going to find this very much in the literature of glasses, but you will find it in the literature of glassy people working in optimization. So when you're doing optimization of case satisfiability and that kind of problems, you undergo these transitions, and these are meaningful in those problems. This is the space of solutions, by the way, at different levels of, for example, difficulty. Okay, so this happens alone. You don't need to put it into your theory. Next coincidence they found is that the actual transition here exactly of the postulated, 50 years previously by Kaufman, which was considered to be the standard of argument for the glass transition. So the reason why was this transition, you are coming, so this is the dynamic there happening, the moment your thing fractures into many, and then you go down, and the Kaufman transition is the moment you're left without any states. So you have reached the bottom. And this scenario, which already existed, is already naturally given. So you have a part already that your model gives you, and another part that the model again gives you naturally, and you can do. So that's very encouraging. Next, you can try to see. Nobody demands that I should work in equilibrium. Okay, here the system falls out of equilibrium, and here it falls out of equilibrium. So if I put it at a temperature there, it will fall out of equilibrium. But it's not impossible to try to solve the dynamics out of equilibrium. I just start with this dynamics at the time 0 and see what happens. Yes?
Can you obtain this TK from an Edwards and this order parameter?
No. Oh, sorry, this what? Sorry,
This transition temperature TK.
Yes, it jumps from 0 to something.
So it's just like SK model?
No, because in the SK it is continuous. It doesn't jump, it's continuous. That's the difference, and this is why it's called random first order. I didn't want to get into that technical, but that's the reason. Okay, so you can do that, and I will show you the equations because they are nice to look at. So you apply these equations. Where are we? So you could do it with inertia or without. It's exactly the same. And above TC, which here I call TD, sorry, you get the mode coupling equations. Below TC, the system never equilibrates. It ages. This is something you discover by solving the equations. You can put them in the computer to start, and then you can solve them analytically. Okay, and let me show you what the equations look like. You get equations that are coupled for the response function, the one I defined yesterday, the response to a kick in a field, chi is the integrated response, and to the correlation, which is the usual spin-spin correlation. These equations, as you see, involve two times. You're not assuming equilibrium. As I told you, correlation and response in equilibrium are related via the fluctuation dissipation theorem. Here I'm not in equilibrium, so I cannot assume it, and indeed I discovered it doesn't hold. And you can try to solve this equation, and indeed you can, asymptotically for long times. At least most of the features you can solve analytically. It's rather surprising that you can solve it, and it takes a while to understand why it is solvable at all. Notice that at long times you need to know all the previous times to go on. And this memory of the whole of your past is nothing. It's not something you can. It's not negligible. You remember the entire past. How are you going to solve for long times an equation that requires the memory of the entire past? It seems like an impossible proposition. In fact, you can, for reasons that are a bit surprising. Okay, when you solve these equations this way, in equilibrium, these equations reduce to these, because correlations and responses are related by the fluctuation dissipation theorem. Only time differences enter. These two equations you can show easily, they collapse into only one. And this only one equation is precisely the mode coupling equation I was mentioning before. Out of equilibrium, this never happens, and you have to take everything into account. And when you take everything into account, you discover that the system below the transition temperature ages forever. To age means, as I told you, to have a solution that remembers the time since it started. And remember what I said about phenomenology. Above the critical temperature, mode coupling already has this property of a plateau in the correlations or in the responses. Fluctuation dissipation, when you plot response versus correlation, holds. And here is where we started guessing that this is the first time it was encountered clearly. When you do the same for correlations below, the solution tells you that this plateau, going down from the plateau, scales with your age, and the same with the response. And this is where everybody became aware from this solution that when you plotted response against correlation, you got these two straight lines. Nobody would have plotted this if it weren't for this solution that sort of hinted at that. So this is where it was guessed.
But the model does have an equilibrium?
It does. It does. It's not unbounded. The one that Bulbul gave yesterday is unbounded from below, so it's natural that it never stops. But this one, the only problem is that the time it takes to equilibrate scales with the size of the system exponentially. And this is solved for times that are long, but always short with respect to the size of the system. So the model has aging, so within all this space has aging, and it turns out, I told you yesterday, that it's quite good. It coincides rather well with, qualitatively of course, with what you get in real life. And it suggests, which are perhaps literally true, they're only true in real life, but at least they are rather well reproduced. Okay, so this is what we call random first order theory. One word. Here I have included spin-like variables, and here I have quench disorder. Now, an objection you should be raising already is, well, okay, but when I do a hard sphere glass, I don't have any quench disorder. My system is just made of spheres. There are no random interactions. Well, turns out that you can make models that behave exactly like this one within mean field without any quench disorder. For example, if you try this model with JIJs, this is a sort of not disorder, sine of ij is divided by n. Think of this as a kind of random number generator or some pseudo random number generator. This one has the phenomenology you want, and it doesn't have any quench disorder. And indeed, the same solution applies to them. So quench disorder is not a valid criticism of this random first order theory. And now I'm going to go to later on to more valid kind of criticism. Okay? So what all these coincidences, and there are plenty, make you feel that this might be the true mean field version or mean field metaphor for a glass. We believe, I mean, we is not everybody, but I think that there's a subset of theoreticians now that are convinced that this is the mean field for a glass. Of course, mean field, as you know, never tells you everything about something you want to know, but it's already something. It has many defects. The main defect, you see it here, this activated region where dynamics is infinitely becomes, you never equilibrate in the mean field version, and the real life allows you to jump and equilibrate. This is the main problem. Okay, so basically this is the story about this kind of scenario. Now the efforts are mostly concentrated. You can get much more out of this. Now the efforts are mostly to take this to finite dimension. Now numerically you can try, but remember that having a numerical model for glasses was never our problem. We have one. Art spheres is already one. The problem for us is to be able to make a theory, and it's proving to be extremely hard to take any of these to finite dimensions. That's true also, by the way, of the Parisi solution for spin glasses. It remains extremely controversial, and because there is no real finite dimensional theory way to do finite dimensions with this. So that's where we are now. Okay, so now, quickly, the question of God gives me a photo of an ideal glass. What should I see in it? So this is what I would see probably if in a God-given picture of a glass. So nothing. So I'm going to. So let me show you a way of measuring lengths of correlation that is, as somebody put it, order agnostic. You don't assume an order you know, and you try to blindly find a correlation. So imagine this is a polycrystallite. So it's the same crystal with different orientations because it's an imperfect thing made of little crystals. And well, now the size of these microcrystallites is easy to see, but I pretend I don't know that, and I want an automatic way to see what is the size. So one thing I could do is take a patch of a given size and see where I find the same patch, modulo rotations and translations. So this patch is going to obviously repeat here, modulo a rotation is going to repeat here, modulo a rotation is going to repeat here. It's not going to repeat if I put it here because this boundary is absent here. But in most places it will repeat, and I will see it repeating very often. On the contrary, this big patch, it's going to be very hard to find a place where such thing would repeat, because this involves the boundaries, which are essentially random, to be the same. And this I will have to go very far to find somewhere where this can repeat. So if I look for patch repetitions of patches of different sizes, there is a critical size of the patch above which it is very hard to get a repetition. That is going to be what I'm going to define. That critical size at which it becomes hard to find repetitions is what I'm going to define as my correlation length. So for here, it's clear that it works. Let me show you it works in cases that are a bit more abstract. So we're going to, this is a picture only, I'm going to take this patch and then see where it repeats, and I increase the size L and see where it begins to be hard to repeat. So let me give you 3 types of levels of order. This is just a game. There's no model behind it. It's just synthetic, let's say. So a periodic thing is a bit like a crystal. You see 0, 1, 0, 1, 0, 1. It's okay. I can make it. There's another form of order that is more subtle, which is the quasi-periodic, which is, obtained by a rule. To obtain this sequence, what you need is a rule where you replace every 0, something like this. I might get it wrong. It might be wrong what I'm doing, but so if you, in each level of this sequence, replace a 0 by a 1, 0, a 1 by a 1, you get a longer sequence, and if you iterate this, you get this sequence, which is called the Fibonacci sequence. And it is quasi-periodic. If you took a Fourier transform of this, you would see a dense set of delta functions. It's something that it is less regular than periodic, but still has a kind of order to it that you don't see so easily. And this is the 1D analog of a quasi-crystal. Yeah. A dense set means that it has to do with this inflation rule. You look at a matrix, and if one of the eigenvalues is bigger or smaller than 1, this classifies whether it is of this category or this one. Just to remind you that this is the way to classify. I can view the paper whether you have this one or this one, but this family here is the easy characterization is that nothing much happens in its Fourier transform. Looks very much as if it were an amorphous, although it is not. Okay, I'm going to tell you why in a second. So now it turns out that if you took a piece here, let me apply what I did before to this one. So I take a piece of this one here, and I see where it repeats. Well, you see that pieces of any size will repeat very often here. That's no doubt. Now let me take this quasi-periodic thing. It might seem as surprising, but here patches are going to repeat rather often. This is not periodic, but why do they repeat very often? Because these were obtained with some sort of inflation rules. So these ones were obtained by inflating very much an ancestor, and any other piece here comes from the inflation of another ancestor, and so you can always get 2 patches rather close to each other that are very similar. This is typical of quasi-crystals. In quasi-crystals, whenever you have a patch, you can find the same patch very, very close nearby. And for the same reason, the fact that there is an inflation rule, you can find that patches repeat here extremely often. So the method that I'm telling you, you see, if I gave you this sequence, maybe you wouldn't have guessed that this sequence was obtained with a rule that is clear and it has a hidden order. You don't know the code of this order, while this one you do know. This one you probably don't. This here with a Fourier transform, you would more or less be able to see something. Here you wouldn't be able to see anything with a Fourier transform. But looking for patches that repeat, you would find that they repeat very often here. In a random sequence, a patch of size L repeats exponentially rarely to 2 to the minus L. Well, here it's order L, simply. Yeah.
I'm just confused. You can certainly define rules, like evolution rules, that will give you chaotic systems, and where you can't find any orders. Is that the kind of thing you're saying?
Whenever there is an inflation rule by which you created your sequence, and in 2 dimensions you have inflation rules to create tilings, you know, the Penrose tiling and all the famous tilings that are quasi-periodic. Whenever there is a rule, this order will exist, in the sense that you don't have to go very far to find any patch repeating. The reason is very simple. Let me show you the reason. It's very clear. I have my sequence here, and I want to see whether this patch repeats this one. Okay, but this one comes from a shorter patch by inflation. This one comes from a shorter patch, And in the end, its ancestor of this one will be a 1 or a 0. But let me assume that this one is a 1 also. Because you had an inflation rule, both were inflated from the same element. So immediately you see that the patches have to coincide. It's easy to convince yourself that you have to go log n up to find this. So it's very nearby that you just try it up and try it down. So to find this patch, rather than taking you 2 to the L, it takes you simply L far. This is characteristic of quasi-periodicity and of any such system. You find motifs, that's the usual word, that repeat extremely often, although nothing is periodic. Okay. So now imagine that somebody came and gave me this. This is a sequence, it's a Thue-Morse sequence where patches repeat, but somebody took these red things, which are just the pieces here, and swapped them. So this is a broken quasi-crystal. How would I know what is the size of the pieces? Well, it's impossible by the eye. I mean, if I swap these two, you're not going to guess much. But now I can do what I did before. I can do exactly the way I started. I can try this. Now I'm in a situation like this one, only that the pieces, instead of being crystals, they are quasi-crystals. So when I get this, I just look for patches that repeat. And again, if boundaries appear, then, or many boundaries appear, because the boundaries are random, I have to go very far to go and look for them. So if I plot the distance, the log of the distance to which versus the distance, how often I repeat, if it's a pure Thue-Morse sequence, it's going to be linear, but there will be a crossover from linear to exponential when I begin to have many boundaries inside my little sample. Okay? The good thing about this is that it is order agnostic. I don't need to know anything about quasi-periodicity, Thue-Morse sequences or anything. This plot, you put it in the computer immediately and you get it. Okay? So I already gave you 3 levels of this. Let me give you one more. These are the Wang tiles. These are famous tiles. I mean, not the original ones, but Mr. Wang was trying to solve some logical problem of undecidability. And the logical problem is, if I give you a set of tiles, the rule is that when you do your tiling, 1 has to face a 1, 3 has to face a 3, and so on. You pay if 2 sides do not have the same number. So this tile matches from above, not this one, but this one, and so on. So can you tile the plane without creating any defects with these tiles? If I give you a set of tiles, you either find that tiling or you don't know. It's undecidable in general. So you may run your program that tries it and find a periodic tiling that does it, and then you've solved your problem. But if you haven't found one up to time t, you don't know if there might be a solution later on. It is shown to be undecidable. Forget about this. These tiles have the property that they do tile the plane, and there is a recipe to do it, and it's very much like the Fibonacci sequence in 2 dimensions. It's some tiling in 2D that has a perfect logic to its apparent disorder. So, but now let me try an artificial example where I take these tiles and I put them in the computer and anneal the problem. So in each one of these squares there's one of these tiles, and I can change them with the computer and try to minimize the number of defects. And I run the program for a while, and I end up after a long time with defects between these 2 faces, These are the mismatches. But the theory tells me that there exists one that has no defects. For these tiles it is proven. Okay, so now I give you this tiling. I have omitted the names of the tiles. I give you this and I ask you, okay, tell me what is the distance between defects. Again, this is a quasi-periodic thing. You can prove that motifs repeat very often, because also the solution of this one can be obtained by inflation, by a rule like that, a 2-dimensional rule like that. And if I choose a patch of this size, it will repeat very often. But if I choose a patch that has several defects inside, it will become exponentially rare to repeat for the same reason. So, okay, this works. And then you can try better and better problems. these are all miscellaneous things. So with particle systems, what would I do? Now, I have my God-given class. I take it to the computer, evolve it for a short time, because I'm not God, but I can still afford a short simulation, just to get the average profile. Remember, now because this was given to me as the true glass transition, there will not be a fall here, and this profile is forever, because by definition this is a pure glass state. And now I look at this profile and I have to see whether patches repeat. Exactly with the same logic. And I would like to prove that patches repeat very often. Or at least more often than exponentially rare, more often than random. Now, you will immediately have an objection. Yes, but this is a continuous thing, so continuous things are real numbers. Real numbers don't ever repeat. So you have to be careful how you define this. This is a big objection, and even of principle. So what do you do? But fortunately, the problem exists already, because when people in dynamical systems count trajectories, there is an interest in dynamical systems to count trajectories. And the log of the number of trajectories is what we call the Kolmogorov-Sinai entropy. But of course, again, with trajectories never repeat. So how did these people come about, Mr. Kolmogorov and Sinai? What did they do? So they proved that if you broke your space into little cubes and worked within a given precision and found the entropy just by saying, am I or am I not in this little cube, then I can define something. And then I send the size of this little cube to 0. And they showed that entropy so defined is well defined. So this, forget about the details, gives you a concrete way to count the number of trajectories or to identify two trajectories. You do it up to a certain precision, and only then you scale the precision to infinity. So what we proposed was to do the same for glasses. I'm going to skip you the details, just to say that I can do it with densities, profiles, and in this way I can do identifications with a given precision and then send this precision to 0. You discover that there is a numerical method to do this, and this numerical method exists already. It was invented for trajectories by Grasberger and Procaccia. It is very famous. It has been used 1,000,000 times, and it's okay. So I thought I was going to give you an argument for why I believe that this length has to diverge in an ideal glass. But I think I'm going to skip that. The only thing I can say is, what would the length be in a glass of those we have in real life? I mean, I take a piece of plastic, or better, a kind of atomic glass. What is the length I expect to see in a glass? And there is this possibility, there is another one. But what kind of length do we expect? Well, in a glass, in an experimental glass, nobody believes that you would see a length of more than 5 interparticle distances. So you see, if something is growing in a glass, it is growing by very little. Now, it is enough to have this length of 4 or 5 to make your dynamics extremely slow. And now, the glass transition problem from the static point of view, the question whether there is a glass or not, a true ideal glass, is whether are you going to go from 5 to infinity or not. But real life manages in all its power to go from 1 to 4 or 5, so it's not very much. So this is where the problem of statics of glasses dies, in a sense. Is it important for you that you have a length of 5 going to infinity ideally, or is it not important for you? Or is it for you indifferent if this 5 will die at 7 and you won't see it anyway, because by then the time scale is going to be... This is a personal question, but it's a legitimate one. The question is legitimate, the answer is personal. 5 going to infinity may sound like something different, because as a principle it says that an ideal amorphous solid exists. 5 going to 7 means that in practice your life hasn't changed a bit, but you shouldn't talk of the glass transition anymore, or you should talk about a glass crossover or something like that.
So the 5 is the coherence length?
It is a kind of coherence length, yes. Numerically, let me say, with the best of efforts, you are with very good luck in 3. So 3, when you imagine that already 2 is a bit unrealistic because it's simply the difference between 2 neighbors, 3 is not something to write home about. But so you see, it's not great. So it would seem that if there is a length that grows, but the time scale grows so explosively with the size that in the end you won't see big sizes and you don't need them. So that's from the point of view of purely equilibrium. On the other hand, out of equilibrium, that's a whole story that is different, and I gave you yesterday all the story of aging and so on. That is there, that you are going to see. And then the only question that is left is, do you age forever or do you age for a long time and then you equilibrate? Well, if that time happens to be 10 million years, maybe you don't care. So that's the other point of view. So I better stop here. If you have questions, ask me, but I think it's not worthwhile to make it much longer. Thank you very much.
There are any other physical systems which are like described by similar physics other than glass?
Yes, I mean, first of all the optimization problems, the most famous NP-complete problems, can in one way or another, your program is a glass. This is why it's hard for it to get to the... So the applications, and there's been an enormous splash, people who were doing optimization this way could give the mathematicians a lot of solutions they couldn't even dream of. Some of them they had, some of them they didn't. Of course, they would never accept our level of rigor, but at least they know what the result is. And then they'll have to prove it the hard way. That's one thing. And then glassiness is everywhere. I mean, wherever a system finds it hard to find its ground state, and this happens very, very often. So look around you, you will find that half of the solids you have around you are glasses. Even those that are supposed not to be, like metals are supposed to be mostly crystals, but once you begin to see that they have defect lines that are entangled and so on, you have a glass of defect lines. And I think that this is going to happen in many, many, many situations.
So everything you've been talking about is classical, and I'm just wondering if is it somehow the case that as soon as we allow quantum effects, this kind of phenomenon sort of can't happen because the wave function will more easily find the
that's a
ground?
very interesting question. There was a time where some people believed that you could have a quantum system at 0 temperature. This Sherrington-Kirkpatrick model put it, the spins in a transverse field and just tune the transverse field. So some people thought that quantum mechanics would help you to cross barriers and find a better. So they tried doing an annealing not in temperature, so you take the system, and it's not that you cool it slowly, but you take h bar to 0 slowly, or something that amounts to h bar. In the case of an quantum Ising model, it's a transfer field that plays the role of h bar. It allows for quantum hopping. So you take the quantum hopping to 0, and these people thought that there's a group in Japan, there's a group in MIT, etc., that this was going to be better than classical annealing. So, as usual with these subjects, while you are numerical, you never know. But the short answer today is that for problems that are thought to be NP-complete, which is almost not factorization, but almost every other problem, it is not better. It is not substantially better. If it was exponentially long to find a solution, it will still be exponentially long. Well, maybe the exponent is a bit smaller, but that's all. We are, I think, despite claims to the contrary, we are now pretty certain about this. And you understand why. If a glass really finds it hard to to find the ground state, would you really believe that putting it at 0 Kelvin and somehow tuning h bar would help it find its ground state? From the physical point of view, it seems completely unreasonable. So I think that from the point of view of really, it's a bit of a failure. But
so is this related to the issue of like speed up of quantum
Yeah.
adiabatic computation and quantum
Yeah.
annealing
Yeah.
and stuff like
yeah,
that?
and this, what happened is that there were many claims at the beginning that, oh, we are getting something better. And then they were simulating larger sizes. But then I happened to participate a bit in this. We showed explicitly in a model that the quantum annealing analytically wasn't giving you it meets a first order quantum transition and the crossing of levels. We had this the other days. The crossing of levels is exponentially, the gap is exponentially small and you're dead. I cannot prove this in complete generality, but in every problem that we have tried, this seems to be the case. So typically it won't work. Of course, for factorization, it does work, but that's another kind of problem. Every problem that can be done with quantum computing, they tell me, can also be done with quantum annealing. There is a procedure of quantum annealing by sending down h bar that does what the quantum computer would do. They are apparently equivalent. And the short answer is that for problems that are glassy, which are mostly, not always, but they tend to be the problems that are thought to be NP complete, quantum annealing is no good. Or if it's good, it's not substantially good.
So one of the quantities to look at when in aging is this correlation function, right, that changes with aging. So what about something like thermal conductivity? I mean, if I look at as a function of aging, I mean, since it's related to like correlation functions in some sense, so that's one question. I mean, how does it change as I look at aging? And also, like, what happens to the Green-Kubo formula in such a system?
So Green-Kubo, what happens is the same as I said about fluctuation dissipation. It's valid. Again, you have to look at the time scales involved, but if you go to frequencies that are low and you're here, you get it with a different temperature. But for many applications, only relatively high frequencies matter, and so you really. But in principle, in a glass, Green-Kubo in total generality is not valid, ever. But of course, for practical purposes, it might be because you might be working or needing frequencies that are high enough. So then you have no problem. About conductivity, the same a bit holds. If the correlations you need for conductivity, and in the experiments I know this is what you need, are correlations that in time are quite close, so relatively high frequencies. So they are rather instantaneous. So in space they are decorrelated, but they are far, but not in time. Then again, a local equilibrium thing is valid, and you don't see much of aging. If you can spot with conductivity in some way or another low frequency fluctuations, then you're in business. We tried. We tried to talk up with the people who do this. Originally Laurent Lévy in Grenoble, and then there's a lot of people who have done these things. It's still ongoing, so I cannot say anything, but for the moment I don't see exactly where we could find the measure to measure aging properties.
So this empty spin glass the model that you showed, so that when you have just two spins, you have a second order phase transition, but the moment you go to 3, it becomes first order. Does it remain first order for?
It is not a first order transition for the energy. It is a first order jump in another parameter, which is the Edwards-Anderson parameter. But in the energy, it is second order. So this is why it's called random first order and not first order. It is sort of a mixed beast between first and second order.
But does it remain the same for like higher number of spins?
Yes. Yes.
It's only when you go from 2 to 3 that does it.
Yes. 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 First order things are more generic than second order in general, and whenever you leave the second order life, you enter the generic world. So that's also typical here. This is why spin glasses are much more rare than glass glasses.
So also another question is whether there is something like an Almeida-Thomas line for these
Yes.
kinds of models, for structural classes. Can you apply a magnetic field? Is that still?
You could, or you could do analogous things where you have two parameters and you have a line of transition, yes.
And so there is something like a replica symmetry breaking.
There is, yes. No, it's not exactly the same. There is a replica symmetry breaking, technically speaking. The transition is a replica symmetry breaking, at least the static transition, but it doesn't take the same shape. For those who know replica theory, in one case it's one step, and in the other case it's infinitely many steps. Or dynamically, in one case you have two time scales, these are the structural classes, and in the other case you have an infinity of nested time scales. So that's the technical difference. Yes?
What will be your take on the debate between droplet model and replica symmetry on finite as?
I don't know. I don't know. What I can say.
Interacting scheme laws with Peter even has apparently simulated. He has probably found out simulation of droplet.
This is a bit like asking in the, I don't know, up to the mid-80s, somebody who went to the Soviet Union, how did you find it? No, you needed to know what was his political affiliation before the answer.
Can you rephrase the question?
I know the question.
There is a debate between the replica scenario. What is a replica scenario? Is saying that what is exact for mean field, it is at least morally correct for finite dimension. And the droplet scenario, which is completely different, it involves only one ground set, let's say, and droplets of the opposite phase growing and so on. And this one, people who believe in the droplet scenario claim that the Parisi solution is only valid in mean field, and as soon as you put one foot out of mean field, it's dead, and it will you are within some form of droplet scenario. There are intermediate people who think that a droplet scenario might be good up to a number of dimensions that depends on the person, and but a finite number, and there's all sorts of people, and there are people who believe in neither. It's a matter of extending mean field to finite dimensions. The literature is immense. It's mostly numerical, and with the same data, or roughly the same data, people claim one thing or the other, or see one thing or the other. Of course, qualitatively, you see features from mean field in real life, as you would. But this doesn't necessarily mean that they are literally true. So I don't really know. Last news I heard is 3 dimensions probably the replica kind of thing doesn't work. 4, it probably looks as if it were working. But again, this could be only qualitative and then not literally true. So I don't really know. Oh, no. 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 What you are dealing with here, that's a purely technical question. What you have to bear in mind is when you have replica symmetry breaking, it means that you have several states contributing many states to your ground state, to your equilibrium measure. These are pockets of probability, just like in a ferromagnet you have essentially up and essentially down. Here you would have different ones, different arrangements, very different arrangements that contribute. There is one that dominates, that has a big chunk of the equilibrium probability, but then there is another one that has another big chunk, and then another one that has a smaller and smaller and smaller. But there are many where different arrangements that can be. Replica symmetry breaking is the technical way in which it appears within replica theory, this fact. But then the actual, how this appears as a breaking of a symmetry, it's very abstract and it's readable, but you have to sit down for a couple of months. Thank you.
photographer is